that seem good? Okay, so you'll get, in fisheries, they'll go out and they'll sample the population. They actually get estimates from catch data. So if they have a number of boats that go out in the season and they get a certain amount of catch, and then they say, okay, we put in a certain amount of effort and we got a certain amount of catch. Because of this relationship over here, we know what this is, and we have an idea of what this is, then you can estimate what this is if you get a certain amount of harvest over a particular point. So you can build up a stock and you can say, okay, last year we had so many individuals. This year, how many one-year-olds came to the fishery? So what you can do is that if you're catching individuals that are age 1, you can examine the fish, and you can actually age the catch. You can say how many one-year-olds do I have, how many 2-year-olds. And they do this by looking at the ear otoliths, and maybe we can have a look on the web later and see how they do this. But you can age the catch. And from all this data of sampling a catch, knowing how much effort went into a catch, and how many fish you caught of different ages, fishery scientists can use this to estimate these parameters. And if they can estimate these parameters, they can estimate what the stock was and what the recruitment was the next year, and they can put a point there. And then they can do this. And they can have a bunch of points. And they can do something like this. Okay? And now they'll say, okay, let's put a curve through that. Well, we know it has to go through 0 because if I've got no fish, no stock, I get no recruits. And recruits can't come out of nowhere, so it has to go through 0. So I could try doing a curve like that as a straight line. Or I could try something like this. Or maybe I could try something like that. Now, these things are very noisy. And whatever you decide to do, let's say we call this f. So what we do is we say x1 at time t plus 1 is some function f of x0 at time t, where f has a particular form. And that form of f is called your stock recruitment relationship. So let's have a look at some of these different stock recruitment relationships. So if I can get this over here. And I'll make this a little bigger. So in the Leslie model, our stock recruitment relationship was just f of s is a constant, and we call that constant S0. That was the Leslie model. So you'll see this includes the opportunity to build a Leslie-like model. Now, in the cohort analysis, what do we do in the cohort analysis? In the cohort analysis, we said that the number of individuals we recruit each year is a constant, and it's the same constant. Remember we said that? And then we made the equilibrium assumption that we get this constant recruitment every year, and we harvest the population in exactly the same way, and we assume knife-edge selectivity, and we assume all these other things. But so the cohort analysis is equivalent to this, except now you've got some age structure effects so that you can have catchability as a function of age, and you can have mortality rates as a function of age, which we didn't have in the cohort analysis. So this would be kind of upgrading the cohort analysis to include parameters that have some age structure in it. Then there's the Beverton and Holt model. The Beverton and Holt model says that there's some kind of competitive effect, so that if you think of the young as competing for some food source, and if there's a large number of them, the proportion that survive is going to be lower than if there's a small number. But there's kind of a return, it's got this convex shape, and it's leveling off, and you might say it levels off at a level that you can call the environmental carrying capacity. So there's just sufficient food in the environment to produce so many individuals, and the more individual eggs you lay, the closer you can get to realizing that environmental carrying capacity. So that's called a compensatory relationship, or you can get this overcompensation, where if you've got a certain number, it grows until it reaches a maximum. And then after that, the individuals are competing so intensely that a much greater proportion than linear are dying, because they're degrading the habitat to the point where if you've got too many, nobody really can mature to a final age. So this is kind of what happens when you get something called scramble competition versus more kind of territorial type of competition. And we'll talk about competition, different kinds of competition when we come to discussing populations competing, like two populations competing, so when we get to our multi-interaction models. And then there's what's called a compensatory relationship, where you start off with a slope that's close to 0, then you get a maximum slope, and then it turns over again. And this says that at very low densities, individuals don't do well because maybe they need some kind of, in fish, the fish are coming together to form groups. And within these groups, they have greater protection from predation than if they're all dispersed. So very often with young fish, predation rates are lower if they can form a group. And these groups will form only if there are enough individuals. So you can get something like that. And for example, in that case, if you plot a s squared over b squared plus s squared, or if instead of using the power 2, you use the power 3 or 4, the greater that you make the power, the more this sort of steps up. It becomes looking more and more like a step function. But you get that compensatory relationship. Okay. So does everybody understand? So if you go through and you look at the way populations are harvested, you'll see that they have these different forms. And in fact, beyond these, so this form is the compensatory form. This is the Ricker form over here. This is the Beverton Holt form. But in fact, fishery scientists have written down an equation called the Doriso-Schnute equation. And this equation has 3 parameters, A, B, and C. And depending on how you choose the parameters A, B, and C, you can get any one of these forms. So in other words, when I fit a model to data, as I have over here, when I fit a model to data, I don't have to decide, is it going to be a Beverton Holt form or a Ricker form or a linear form? I can take a 3-parameter model, and I can fit the model to this data and see which form it gives me as the best fit. And the way you do this is using nonlinear regression techniques. So you've learned how to do linear regression techniques, but nonlinear regression techniques can be done in a similar way. And what you're measuring is the distance of the line from the points as the residuals. So this point over here, that's the residual of the fit. That's the residual of the fit. Because you're interested not necessarily in whether it's positive or minus, you just square them. And then you look at the sum of the squares of these residuals. And the fit that gives you the smallest sum of squares of the residuals has some nice statistical properties that are used to help fit these models. But the different concepts for fitting data. This is called the least squares method. And so you can do that. But this is not a statistical class, and so we're not going to go into that in too much detail. Now what we're going to do is we're going to talk about calculating the yield. So are there any questions about this material so far? So behind here we have this equation, which I'll write down again. dxi dt is minus alpha I xi minus qi v xi. This is the natural, and this is the fishing mortality rates. And this whole thing over here is the harvest rate. So if we have a look and we want to calculate the harvest, and this is what I'm doing here is I've got a harvest, and I'm calling this y, what I get from the ith population. In this one, I'm using k instead of t plus 1 because I'm integrating with respect to t. But we're integrating from t to t plus 1, and your variable that you integrate over, here we've got qi, v, xi, and the dummy variable we can name something other than t. We can tau, d tau. There should be a dt over there that's missing, but yeah. So you're integrating this. So if you write down the solution, xi at t that we got, you can actually do this calculation. I'm not going to do it. So you can write down xi at t. You can replace it with xi at, if you're going from k to k plus 1, then it'll be xi at k. Integral from k to 1 or just the exponential part, and t goes, and you're just going from t equal to k plus 1, or in this case, tau going from t to t plus 1. And so you go through and you do the integration, and you can integrate that, and you can get the expression. And then to get total y, you have to sum this over I. So you sum this over I. Yeah.
So is that a very tau and then
Yeah. xi. So I'm integrating over tau d tau, tau going from t to t plus 1. Here I'm integrating over t going to k plus 1. These are all just dummy variable names. The thing is that I've taken a bit of text out of different places. So you get an expression, and if you notice, this harvest term over here depends on v. So like in the cohort analysis, it depended on v and the critical time. Here it depends on v and your catchability coefficients. So your catchability coefficients are now telling you about the effect of your gear. Whereas in the cohort analysis, the effect of the gear was it didn't affect the population until the critical time, and then it did. Now the effect is through the catchability coefficients. And so you can build a model, and if you know where your fishery is at a particular time, you can calculate this yield. You can also do an equilibrium yield effort analysis. So I can say, if I choose a particular value of v, what's the corresponding equilibrium harvest level? So to get the equilibrium harvest level, you can either solve those equations to find the equilibrium, or you can harvest it until the population goes to equilibrium and then see the rate of removal when it goes to equilibrium. So you've done those kinds of simulations in your harvesting study. And if you do that, you can show that for different catchability coefficients, you can get different kinds of curves. So if we go to the homework over here, so what I say to you, okay, here's the model. And in your homework, I'm doing it in terms of k to k plus 1. Why isn't it showing up here? Let me make this bigger. Okay. So I say consider this fishing model. So I'm iterating over k. I start at k equals 0, and I get my initial values for x1, x2, x3 at time 0, and then I can calculate x1, x2, x3 at time 1 as k iterates. So I can iterate over k. And if I've got 5 age classes, this is the first, second, and third. Here I've got x0, which is my stock index, and I've used the Beaverton and Holt type of stock recruitment function. Can everybody read that, or was the resolution not good enough? Okay, so you can see. So this goes for I equals 1, 2, and 3 on the left-hand side there. And this is the stock index. And then in terms of the alpha and the Q's and the V, I can calculate the harvest, and this is the equilibrium harvest that it would go to. So I can take this population, I can start out at a particular value, and I can iterate it for V equal to 0, or V equal to 0.1, or V equal to 0.2, and I'll get to an equilibrium situation. And then at that equilibrium situation, when the population is not changing anymore, then Y will not change anymore, and that I can say is my sustainable harvest. Then what I do is I do that, and when I do that, for different values of V, I'll start off with V equal to 0, V equal to 0.1, 0.2, 0.3. So that means I have to run my model 10 times for each unit of V. So I run it 50 times, and I can construct this curve, where this curve corresponds to one set of catchability coefficients. And the second curve corresponds to another set of catchability coefficients. So in this model, I'm giving you 2 sets of catchability coefficients. Let me just get a smaller version. Yeah, so I'll say, this is a rich anchovy fishery off the west coast of southern Africa. And so this is actually data from a real fishery that I studied in the 1979, 1980, or 1979 before it came to the United States. when I still had a South African accent, which I don't have anymore. Do I? No, I know I don't sound completely American yet. One day. Okay, so this is a rich anchovy fishery of the west coast of southern Africa. Has been modeled by the above equations. And here, the parameter WI and BI are the same. So BI equals WI, except for B1. So what I'm saying is that the fecundity of individuals is proportional to their weight. So this is a relative index, except when they're 1-year-olds. And in that case, I put a beta in front because that represents the number of individuals that are mature by the time they're 1. And if you assume beta is 0, they're not mature. If you assume beta is a half, only half of them have matured, or they're half as mature as you'd expect them to be if they were producing eggs in proportion to their mass. That means that they started to produce eggs, but only in a small quantity. So there's a possible case of beta being somewhere between 0 and a half. Then I give you all the W values, and I give you the A value and the K value and the alpha value, and I give you a set of catchability coefficients. So I say Q1 is 0.16, 0.24, 0.28, 0.67, 0.67. And then I say verify through simulation that the unexploited population. So you put V equal to 0 in there, and you run it, and you show that the equilibrium level you reach is given by this number, where the units are in billions. So the trick about doing this is to get your units right. When you put in these parameters, I recommend that you don't just put in the parameters like 1, 2, 2, and then 9 zeros afterwards. You actually work in units of metric tons, not in units of kilograms. These units here are kilograms, or there are billions of, you can work in millions of individuals or billions of individuals instead of individuals. So you can get rid of a lot of these parameters if you're working in the right units. So here I say the units of X0 are metric tons. So if you work with these units, you'll be working with metric tons. But you can convert, so you're working in thousands of metric tons, because the answer turns out to be in thousands. And here, when I say these are the number of individuals, these are units of billions of individuals. So the real sticky thing is to get the units right. So make sure you put in the numbers so that you get the units right. Then I say if the current state of the stock has this particular level, which you see here, 28, 2, 1, and 0.2 is different from 115, 111, 50, 22, 10, and 8. So if you looked at the stock, what would you say about it? If you compared it to its equilibrium value over here, when there's no harvesting, what would you say when the stock is in this state? How big is it compared to its equilibrium value? Yeah, it's about, well, the 20 is less than a fifth to a sixth of 111, but 8 is also about a sixth. So basically, it's in a highly exploited state. So then I say, what is the corresponding stock level index X0? So if this is the case, you have to calculate X0 by doing this calculation over here. That gives you X0. And how long does it take the stock to reach 90% of the equilibrium value X0 had? So what you do is you calculate here, what would this be at equilibrium? So at equilibrium, X0 would be something. You take 90% of that, and you say, if I start off at this level and I use my model, X0 is going to grow every year. How long does it take to get to 90% of the equilibrium level that I get when there's no harvesting? And then I ask you to construct a sustainable yield effort curve for the case when beta is equal to 0.5. And I ask you to construct a sustainable yield effort curve if beta is equal to 0. And I say, what is the value for VMSY? So if we go to the previous, you'll see that in this situation, the V that maximizes your sustainable yield is this value over here, V equal to 1.1. If this is curve A was gotten with a certain set of parameters. Now, this is just a picture. It's not necessarily the exact set of parameters that you're going to have in your homework. But that's what you do. You construct the yield effort curve and you say, what is the value of V that maximizes? In B, you see that the value of V that maximizes your yield, as I increase V, I get more yield. So maybe that the maximum sustainable yield you could only get with infinite effort. So it depends on your yield effort curve, what case you have. And the case you have depends on your catchability coefficients and the parameters. Yes? That beta. Yeah, that beta says that I'm assuming that an individual's fecundity is proportional to its weight, except for the lowest age class. In the lowest age class, I'm saying it's not proportional to its weight. I have to modify it by a factor beta. So what I said is that, yeah, I'm going to make BI proportional to WI, except for B1, which if none of the individuals are ready to reproduce at age 1, then beta is 0. If individuals are only producing at a rate proportional to half their weight rather than proportional to their whole weight, then beta would be equal to half. So it's a way of setting the relative fecundity of X1 compared to X2, X3, X4. You might say, the reason why I say relative fecundity, because there's another parameter here in the stock recruitment relationship, and that's the parameter A. So if I come to this curve here,